Okay, let me review this one more time so that you have a little video for it. If my airplane is aligned along the IV axis like so, but it's flying along the red air path axis, then the airplane will fly like this. It will have both an angle of attack, which is in the aircraft vertical plane, so you have to get rid of the beta first, and then come in the aircraft vertical plane to find AD, then rotate that up in the aircraft vertical plane to get alpha. The alpha dot is out the right wing. If I want to get beta, then I generate my KS factor. My KS factor over here, I'll rotate about that, so beta dot is going to be along KS, and that will rotate S out of the board to air path, giving me positive beta. So how would a pilot remember positive beta? If you remember wind in the right ear. If I have wind in the right ear, I have positive beta. Don't give me all the stuff about the beta dot vectors. Just wind in the right ear, I get positive beta. How about positive alpha? Wind in the butt. If you got wind in the butt, you got positive alpha. Forget all the vectors. Those are the two criteria. Wind in the left ear, negative beta. Wind from the head, negative alpha. So this is the notation that you have. And then if you wanted to use coordinate transformations, these are some of the relationships that I would expect you to know and be able to develop. How the transports can be used to go from the A system to the B system, or from the B to the A. And if you want to remember why this is important, so you know the aircraft stalls when alpha gets too high. And notice that, remember, I'm not hooked up to the earth, so I can stall the airplane like this, can't I? If I'm in this attitude and I pull too much alpha, I'll stall the airplane. So that's something to remember. I don't have to be flying like this and stall the airplane. As long as he's below maneuvering speed, if he's above maneuvering speed, then he won't stall, he'll pull the wings off. But when he gets to the stall angle of attack at maneuvering speed, he'll stall the airplane right at the structural limit for the wings. So you should remember what maneuvering speed is, max G load, how that relates to the minimum radius of turn. All this is kind of being tied together now, and then how it alpha. Now, how does beta work into this? Well, airplanes don't like beta. Right? You don't like beta. So how do you know that you have beta when you're flying an airplane? They give you a little instrument. Pilot, Zach? What's the instrument that tells you that your beta is not zero in the airplane? How do you get turn coordinator in the airplane if you're flying? What do you look at? You see that? There's a ball in the race. Right? There's a little ball, and then you're taught to step on the ball, right? So if that ball, you have a little ball that's in a race, this is what it looks like in the airplane. I'll take a picture of it like this, and the ball sits right in there. And you can think of yourself as the ball, right? As yourself. So if that ball moves like over here, that means that you should feel your right shoulder being pushed against the right door. And that's because the lift vector isn't right over your head. So you step on the ball, and if you step on the ball, that will move the lift vector back over your head, which basically means beta is zero. So if this ball is pushed to the right or to the left while you're flying, that means that you're in an asymmetrical condition that's generating beta, and the airplane doesn't like that. If you generate too much beta, what happens? Well, in a small airplane, the airplane will tend to roll. You'll have to hold opposite control to keep the airplane from rolling. You'll see too much relative wind on one wing versus the other. Fighter airplane like this, or a F-4 or a F-18 or a modern aircraft, too much beta on that airplane will depart the airplane. It will go into a spin entry automatically. Weird spin entry, sometimes inverted, sometimes uncontrollable. I mean, where it's actually too controllable. It's too stable. It enters a too stable a maneuver that you can't get out of it. So a spin is actually too stable of a maneuver. You enter a maneuver you can't get out of. We call it uncontrollable, but uncontrollable would be kind of like flailing around. A spin is a maneuver that is tightly constrained by how the aircraft is moving, but the flight controls aren't having any effect to get it out. So too much beta, that's how you enter a spin. You go up, stall the airplane, you step on the rudder, boom, cause all this beta. That beta tends to topple and stall the wing, and you enter into what's called a spin. So beta is bad. The alpha and the beta generate the forces and the moments that excite the equations of motion. That's how it works. If I want to find omega b slash AB, do I know omega b slash A in any coordinate frame? Well, it looks like omega b slash A in any coordinate frame. Let's suppose I have omega bs in some coordinate frame, and then I added omega. This takes me into A into S from A. Would that work? So I have omega from A into S, and I have omega from S into B. By relative angular velocity, that should give me the angular velocity from A into B. Everybody with me? Michael, you with me? Yep. So just relative velocities. Okay, do I know omega b slash S in any coordinate frame? Yes, I do. I just derived it up here. So I can put omega b slash S in here, and I know it in the stability axis coordinate frame. Do I know S slash A in any coordinate frame? Yes. Yes, I do. I've just done it over here, except it's the reverse. So this must be 0, 0 minus beta dot if I were to flip these two around. So I know S slash A in the stability axis. So I know these two guys. I can substitute this directly into here, the negative of this directly into here, and then I know omega b slash A in the S system. How do I get it into the B system?
Cosine matrix.
Direction cosine matrix. That's what direction cosine matrices are for. So I'm going to go C. I'm going to go make this clear for you. I'm going to go C into the B system from the S system. I know. But do you see how it works?
Yeah.
You know, and how do you know this system? Well, B stability axis to the body system through alpha. We did that yesterday with the atmospheric rectangle. Okay. I like this problem because it gives you an idea of what the test is like, one. And two, it shows you how to solve seemingly difficult engineering problems, right? What's the first step to solve a difficult engineering problem? Divide it into parts.